Intelligent Transportation Systems Podcast. Welcome to the ITSPodcast. This is episode 14 for June 2014. I'm Javier Sanchez Medina from the Intelligent Transportation Systems Society. We are back online with a new episode for your entertainment. We have a very instructive three-way interview with two researchers based on Australia, Professor Eduardo Nebot and Dr. James Ward, on a very interesting work to be soon published at the ITS magazine about the Warrigal Dataset, a fascinating dataset that may prove really useful for many researchers soon. Additionally, we do have a transportation in history about one of the most ancient transportation means, horses. Finally, we have a striking new regulation at California regarding autonomous vehicles that may become historical, allowing automatic vehicles circulating merged into regular traffic. So that is the plan. Please get comfortable and relax. We'll start now.
This is the news mini section for episode 14, June 2014. California is one step ahead again. We have recently learned that the California Department of Motor Vehicles will be granted driving licenses for, wait for it, autonomous vehicles. Yes, this is happening, you are not dreaming. From September 16 on, anyone in California can apply for a special license for driverless cars and become the human co-pilots. Even better, the cost of this new type of license will not be a limiting factor at all. Only $150 each will cover up to 10 vehicles and 20 test drivers. Of course, the requisites to obtain those licenses will be pretty hard. For example, each car needs to be insured for at least $5 million against personal injury, death, or property damage. The test drivers must prove their competence with a full clean record, and they must be able to take full control of every autonomous car immediately in case of emergency. We have included a link to all the details in this new regulation in our podcast website. Anyway, once all the requirements are satisfied, we may drive along with autonomous cars in the whole state of California. This may be a historical milestone for autonomous driving. So remember the date, September 16, 2014. Finally, a short advertisement. Next October, the flagship conference of the ITS Society will be held in Qingdao, China. The call for papers is still open. It has all the ingredients for an amazing meeting you cannot miss if you usually publish in our conferences. Search for the call for papers link in this episode website.
Transportation in history. Horsepower. Have you ever thought about the origins of that power unit? Horses. If you like horses, you're gonna like this section today. Horses are one of the oldest and most widely used transportation means ever. It is believed that humans started domesticating horses at around 4000 BC. Since then, we have created more than 200 breeds, from the powerful Clydesdale to the graceful Arabian. It is a fascinating species indeed, and our fascination for it can be visualized in the extensive collection of words we use for all the things dealing with horses. We include in this episode post a link to a glossary about equestrian terms as an illustration of this fact. It is estimated that more than 100 million horses, donkeys, and mules are currently used in the world for agriculture and transportation. In the United States alone, the impact of horses in the US economy was nothing less than $102 billion according to a 2005 American Horse Council report. There is evidence on that the first domestication of horses happened in Central Asia, probably in Ukraine and Kazakhstan, for pulling chariots. It is believed that the first horses were too small to carry people, and it wasn't until they had been bred bigger that people could ride them. By about 2500 BC, the Sumerians in West Asia were already using horses and wagons. They probably were essential to their expansion all through Europe and Asia, helping them both as means of transportation and as a warfare advantage. There are still scenarios today where horses outperform any other technology, like certain types of patrol duties and crowd control, cattle ranches, rescue services in difficult terrain, usually mountains, etc. Additionally, there is a tendency these days to get back to their use in reserves or wilderness areas where air pollution or sound pollution are undesirable due to the ecological value of the area. So don't be surprised if one day we go radical about making our transportation truly greener and we return to that beautiful zero carbon dioxide emitting vehicle that can do something even the smartest cars can't. Be a good bet. Hello again, let's start now with the main course of this episode, our interview to Professor Nebot and Dr. Ward from University of Sydney. It has been a really technically challenging one. The sound quality is not the best, but the information shared is so interesting that we are sure you will enjoy it anyway. Here we go. Today my guests are in the biggest island in the world, to be precise, in the Australian Centre for Field Robotics, in the University of Sydney. A group of professors and researchers from that centre down under are publishing a very interesting work at the Intelligent Transportation Systems magazine, titled the Warrigal Dataset, Multi-Vehicle Trajectories and B2V, Vehicle-to-Vehicle Communications. Two of them, namely Professor Eduardo Nebot and Dr. James Ward, have kindly accepted participating in this interview today. They are well-known colleagues in the field. Let me welcome our guests. Hello, Eduardo. Hello, James. Can you please introduce yourself to our audience? Can we, for example, start with you, Eduardo?
Okay, hello Javier, and thank you for inviting us to participate in this session of the ITS podcast series. I'm Eduardo Nebot, and I'm a professor at the University of Sydney at the School of Aerospace, Mechanical and Mechatronic Engineering. My fundamental areas of research cover sensing, automation, navigation, and safety with applications to mobile and field robotics. I'm currently the director of the Australian Centre for Field Robotics, and I've been involved in many automation and autonomous projects for the last 20 years. In particular, in the last 10 years, I've been working with my team in a number of projects involving intelligent transport systems in the areas of communication, mapping, driver intent, and safety.
Great. How about you, James?
Hello, Javier. It's a pleasure to be talking to you. I'm a researcher working at the Australian Centre for Field Robotics as well, and I work in Eduardo's group, the Intelligent Vehicles and Safety Systems Group. I'm interested in vehicle safety through improved situational awareness, vehicle-to-vehicle communication, and closing the feedback loop to drivers. I'm focused on developing proactive measures that can improve safety by anticipating and avoiding bad situations rather than having them happen and reacting to them.
Mm-hmm. As I said, you both work at the Australian Centre for Field Robotics. Can you please describe how is your centre like? What kind of research do you develop? I'm curious on how comprehensive is that field robotics in its denomination.
Well, the center was created in 1998 by 4 academics at the School of Mechanical Engineering. It currently has more than 170 people, that with 6 academics and more than 40 researchers and probably more than 40 technicians and approximately 60 PhD students and administration personnel. The fundamental areas of research are perception, control, learning, and systems, with application to field robotics in land, air, and sea domains. The ACFR Center is well known for the fundamental and applied contribution to field robotics, with a significant impact in various industries such as mining, stevedoring, and aerospace. The center also has a very strong link with industry that provide approximately 90% of the total yearly budget funding, that is approximately in excess of $12 million.
Wow.
We created a center with a mission to build an autonomous field robotic industry in Australia. This country is very well known for the utilization of very large machines operating in very difficult environments, such as mining. It is also has an important stevedoring industry that 10 years ago was willing to invest in automation. When we started the center. One of our landmark projects was the design, development, and deployment of AutoStrad. This project consisted in the full automation of 60 tons straddle carriers. This, just to give an idea, these are the machines that move containers in the port. And the project was, at that time, was very challenging because we needed to control these machines with an accuracy of the orders of 3 to 5 centimeters. Today, we have ports with more than 30 straddles working completely autonomous. And it is fair to say that this is potentially one of the most sophisticated autonomous operation in the industry working today. The center also hosts the Rio Center for Mining Automation, this RTCMI. This is also a multi-million-dollar project that has been running for the last 7 years and is responsible for the fundamental concept of the mine of the future. That includes the automation and many other areas. We host the Quantum Center for Flight Optimization since last year, and it's going to be running for a few years. We also have important research groups working in agriculture, underwater, and unmanned air vehicle. It is fair to say that the center, the Australian Center for the Field Robotics, is one of the leaders in the world in field robotics for industrial application. This is basically just give a brief overview of the project in field robotics performed by the center.
That's pretty impressive. James, do you have anything?
Okay, yep. I became part of the center a little over 2 years ago. I joined the Intelligent Vehicles and Safety Systems group with a view to working on problems in safety monitoring, evaluation and reporting. But in the short time that I've been with the Australian Centre for Field Robotics, it's clear that the strongest emphasis is on field robotics. Doing things like making data sets from actual field deployments, such as the one we're making available in this publication, to the wider community is an important way to further this research.
Mm-hmm. Good. Okay, that's great. Let's get back to that paper, the Warrigal Dataset. Could you please describe what is that dataset and how can it be useful for our researchers?
Okay, I will start with an introduction. To this idea. As mentioned before, the center has been involved in many industrial applications, and it is by working in this project that we discover new research challenges. The demonstration of this application usually requires large deployment of technology, significant resources from the industry, and in many cases sophisticated pieces of equipment. These constraints makes the possibility of acquiring this sort of data limited only to a few groups. In this case, we have a large fleet of vehicles retrofitted with vehicle-to-vehicle communication operating in an industrial environment that is changing with time. What we are meaning that the changing with time, that is a dynamic environment in which new roads are being built continuously. The data collected allows us to make contribution in many areas, from mapping, safety, equipment monitoring to driver intent. We strongly believe that having a full documented data set shared with the research community will enable many new lines of research, and as well as it provide new tools for proper testing, comparison of the performance of new algorithms. We have experienced this in the past when we released a very important data set that was the Victoria Park data set. This was very popular because it was used during almost a decade with the research in simultaneous localization and mapping. And I finish and now continue, James, with the details.
Okay.
To give you some idea about the dataset we're releasing, here are some of the key features. The dataset was gathered from a fleet of vehicles operating in a quarry type of environment. As it was an industrial environment, we have a mixture of different vehicle types with vastly different dynamics, from regular-sized four-wheel drive cars up to massive trucks hauling the ore from place to place. Those trucks have very poor visibility from the driver's cabin and obviously a huge amount of momentum as they drive around. That was one of the motivating factors for this project in the first place, helping the drivers interact safely with all other types of traffic that they encounter. Communication of vehicle state was a key component of the system, and as such we've logged a vast amount of very high frequency data. The data forming the dataset that we are releasing includes, we have position and velocity information for each vehicle, records of the radio messages sent between them as they meet. We also have information about which vehicle antennas sent and received the messages, the signal strength of the receiver. To give you some idea of the scale of the dataset, we have around 3 years of data at a resolution of 1 Hertz. We've put 3 months of data up on our group's website, and we're happy to release more if researchers ask for it. We'd put it all up there, but it would be a truly massive dataset if we did that. A typical day's worth of data involves 18 vehicles driving a total of 3,000 kilometres on around 150 kilometres of roads, across 65 square kilometres of quarry site. We've also provided maps of the area because, as Eduardo mentioned, it's so dynamic. The roads move around as the quarrying operations change the environment. In fact, methods for generating high accuracy maps from this sort of data is one of the things that our group has been exploring. We've also used this data set for online determination of antenna failure, evaluation of safety metrics and trends over time, fleet tracking and prediction when outside base station coverage. There's a vast number of applications for this data, and we hope that other researchers will find uses that we haven't even dreamed of yet.
Okay, James, I think the name of this data set has a history behind. Can you please explain?
Certainly. Warrigal is an Australian Aboriginal word for a native dog, for a dingo. And dingoes cover vast distances as they move around their areas, and we thought this would be an appropriate name for a data set that describes vehicles traversing vast distances in the Australian outback.
Is it a dangerous animal?
Certainly it's not an animal that I would want to spend a lot of time with. I think there are more dangerous animals in Australia, but they don't make particularly good pets.
Okay, that's great. Can you please explain what you mean by driver interactions? Is an interaction when vehicles are close together, or is it a more formal coordination?
Okay, I mean, for the past 10 years, we have been involved in safety application for the mining industry. The approach that was designed was based on how we envisage future autonomous vehicles will be integrated into existing fleets of vehicles. In an industrial environment, vehicles will always need to interact to achieve a collaborative task. One example is the interaction between a loader and the truck. I mean, that in a quarry type environment. At the urban street level, we can see the interaction of vehicles at an intersection, at the parking lot, or in any areas where they are moving together. We believe that the interaction problem requires the vehicle to be completely aware of all the vehicles in proximity. This must also be achieved with high level of integrity in order to be able to interact in a safe manner under all possible conditions. And when we refer under all possible conditions, it's because we need to assume that we need to interact safely, independent if it is a nice day, independent if it is raining very hard, snowing, or whatever. We call this concept, of high integrity situation awareness. And this concept requires 3 fundamental components in order to be achieved. One is positioning, the other one is vehicle-to-vehicle communication, and the third one is perception. The idea is that all the vehicles in proximity become aware of each other by communicating their position to each other, And also, the integrity is achieved by including the perception in order to verify the existence of the other vehicle in proximity. This is the concept of integrity. The fundamental idea is since position, that is communicating through the vehicles, and then the other vehicles are able to perceive the vehicles with their perception sensor, it's very unlikely that these two methods of detecting each other will fail at the same time. This dataset has information regarding position and vehicle-to-vehicle communication. At the simplest level, we can infer situation awareness by using position and vehicle-to-vehicle communication. We can also develop much more sophisticated algorithms in order to get routes, driver intent, map, and context. This information obviously improves the knowledge of the current state of the world. And it is with this intelligence that allows us to make much more accurate inference about the risk and the safety of the current and immediate task.
James, do you want to add anything?
Yes, please. In the case of this dataset, we are calling it an interaction when the vehicles are close enough to communicate. As Eduardo said, we are trying to make drivers aware of the presence of others. When this information is made available to the driver, we would expect him to change his behaviour based on this information. So in that sense, he is interacting with other vehicles as he is behaving in a way that takes account of the other vehicle's presence. All of the vehicles in this dataset are completely human controlled. There was no control of the vehicles by a control system for things like platooning. But the issues we've been addressing here are necessary for coordinated action in the future. You need to know that the vehicles around you have reliable antennas if you want a platoon, for example.
Very well. And Eduardo, what types of interaction can be predicted, and what is the time horizon for the prediction? Do you envision long time prediction or shorter seconds prior to interaction?
Okay, Javier, these tools were initially designed for analysis, that is to replay and verify the operation of the different components. Once we start working with these tools, it soon became very clear that this information was unique in order to study and potentially predict interaction and driver behavior. Under the point of view of safety, it could offer information about the different level of risk that is actually taken by the driver. For example, let's imagine that in an operation you set rules that no two heavy vehicles should get closer than 40 meters. Then, with this tool, we can analyze how many times this rule is actually broken and where in the operation is actually this rule is broken. This, with this information, you can actually introduce changes to the road design, generate or produce more signage, in order to avoid, breaking the rule, or basically perform more training to your operator. In the past, the only available information were the accidents. That accidents are really very rare, and sometimes, with severe implications. We can now have these tools to monitor the safety of the operation based on the metric that relates to the potential accident, but these metrics, this information occurs much more frequently, and we can measure, and we can evaluate, and we can take actions. In terms of prediction, we have done significant research for long and short-term prediction. We have a number of publications addressing long-term prediction by one student of mine, Maya Shan, and also Stuart Warrell, that combines the models of the vehicle, also the vehicle profile in the road map, and intersection model in order to be able to predict, to make long-term prediction of the vehicles in a fleet. Also, we have done significant research in short-term prediction, and this was investigated for driver intent purposes. This is a very important area for research for us, and hopefully we are going to comment more later about this. And also to select model for vehicle motion prediction. We use the fact that the constant velocity model are no longer valid. That in the case a vehicle is detected another vehicle in an intersection. So basically, we use basically vehicle-to-vehicle communication in order to select the proper model in order to use in our statistical filters. So probably now James is going to talk more about this type of interactions.
James?
Yeah, thank you, Eduardo. We've been doing a lot of work on predicting driver intent. What do we think the driver is going to do in the near future? Generally, we would be interested in time horizons of less than 30 seconds when we're looking at predicting conflicts between vehicles. But we have done other work, as Ed mentioned, where we look to predict the movement of vehicles that we can't observe directly over time periods of minutes at a time. Because we have second-to-second information about the vehicles, you can use this dataset to refine algorithms at any time scale. For example, you could observe the information of a vehicle as it approaches you at an intersection and make predictions about whether it is likely to turn across your path or continue straight ahead. Because you know what the vehicle actually did, you can compare your prediction to the ground truth. And you can do this over whatever time horizon is appropriate to your application. So you could be looking at the movement of vehicles on an hourly basis, on a day-by-day basis, on a weekly or monthly basis. We've done analysis at all of those levels, but because of the level of detail in this data set, you can essentially choose what it is that you're interested in.
Great. Well, I need now to make a very short break, but we will be back in no time, so please stay tuned. Hello again. Do you want to get a warning to your email with every new podcast? It's easy. Visit ITSP.cicei.com. There you can subscribe by entering your email address both at the right side widget or the bottom right follow tag. Once introduced to your email, you will get a confirmation message where you should click in the activation link it contains. However, if you are more like the kind of smart apps fan, you can search for this show at your preferred podcasting application. Search for the keywords intelligent transportation and you will find us. Remember, intelligent transportation. Thanks for listening to ITS Podcast. Let's get back to our interview. Very well, we are back again with our Australian-based researchers talking about that interesting Warrigal Dataset. How is that database created? Who and how enter the information there? Eduardo?
Okay, well, at the moment we are generating the information and uploading different databases, including the information used for this in this particular publication. It remains to be seen, that which will be the best approach for others to include other data sets, perhaps using the same database, or basically us including different ways of uploading the information. I will leave up to James in order to explain in more details the actual procedure.
Okay, thank you, Eduardo. The database started its life in individual logs created on each of the vehicles. The quarry was fitted with a limited number of fixed base stations at high traffic points, what we would call roadside equipment in the ITS world. These base stations would opportunistically harvest the logged information from the vehicles as they passed. So we would often place these at areas like parking areas or intersections that had high traffic most of the vehicles would go through. This information was integrated into a single database that forms the basis of the data set that we are releasing. It's interesting to note that in this scheme, vehicles that did not pass the base station regularly or even at all could still be monitored as other vehicles would interact with them and then report these interactions upon their return to the base station. Given the literally millions of data points in the database, the population of the database was entirely automated. But we can then export whatever periods in time researchers are interested in and make it available in a number of formats. At the moment, we've provided just plain text, comma-separated value files so that other researchers aren't tied to a particular platform. But as Eduardo was saying, this is a new experience for, I think, all of the community. So over time, we might find that there are ways that are more suitable or easier for people to use.
I see. And the information, is it processed or is just provided raw? I mean, does that database provide with data mine products or only raw data?
Okay, well, we provide the raw data, and we'll be publishing algorithms that make use of this data and new data as well in the site. In fact, the last few papers submitted to the magazine and to the ITS journal included code and the data set to encourage further research in this area.
Anything else, James?
Yeah, I can go into a little bit more detail about the actual information that we have there. The state information of the vehicles and the interactions is provided raw. By that I mean that the positions, the velocity, GPS information like dilution of position, the radio communications and signal strength are all presented directly as they were recorded by the vehicles. As I mentioned earlier, we also have some high-resolution maps of the operational area that are provided in the dataset. These were generated using techniques developed by our group to take position information from the vehicles and make useful maps. In the paper with the dataset, we have actually mentioned some of the work our group has done with this data. All of that work has a common factor of data mining and exploiting the dataset to extract more information. So in that sense, we've also provided products that have come from the dataset. For example, this work has included such things as determining trends in safety metrics over time, or by vehicle class, or by road type. Creating studies that look at aggregate measures from the data is definitely possible. As Eduardo mentioned, we've also included some MATLAB scripts that can load the data and play it back in real time. It's nice to see the vehicles driving around on the screen, but it's also a useful basis for any further analysis that people want to do. You don't need to worry about writing routines to load the data. You can just take our scripts as a basis and the data will be loaded for you, and you can apply your algorithms directly to that data once it's loaded.
It's pretty interesting. Okay, and can it be used online in real test, or has it been used like that?
Well, as mentioned before, the database has been used as an offline tool to analyze the data and to generate useful information in order to improve the situation aware aspect of the fleet of vehicles interacting in an area. Saying that, I mean that there is nothing that prevents using this information in order to make additional inference in real time in order to assist the driving task. In fact, one of our current areas of research is looking at building intention maps from different data. So the idea is just we have an area and we have a full map of driving intent in this particular area. In this case, the database could be augmented with this map, and this information could be used in order to implement real-time safety. For driving assistance, as an example. No?
Do you agree with that, James?
Yeah, absolutely. We haven't used the data in online testing, such as in a simulator, but the information in the dataset was used to provide real-time feedback to the vehicle drivers about their behaviours and to improve their situational awareness. The systems and the algorithms that we use to do this use nothing more than the information we provided in this dataset. So in a way, this data has been used in a real-time test.
Mm-hmm. Vehicle-to-vehicle communication. How do you see the future of automation with this regard? Can our future private cars effectively communicate between them without any infrastructure around?
Okay, well, probably, I mean, that we'll keep talking about this during the rest of this interview, but something is that there is no doubt that vehicle-to-vehicle and vehicle-to-infrastructure will play a fundamental role in the deployment of autonomous vehicles. We have now already a large number of testing experimental sites of this technology, and some of them actually consider more than 3,000 vehicles, like the IntelliJ Drive in Michigan. This is a testing of a site, for a testing experiment for this technology that was organized by the State Department of Transportation in US. We also expect that new vehicles will start to be retrofitted with the standard communication technology, in this case the DSRC technology. And basically this will be use it initially in a vehicle-to-infrastructure application, but then that it will become a common vehicle-to-vehicle application. We believe that the introduction of autonomy will be progressive. That with some level of assisted automation introduced in the first stage. Then, that after a while, there are going to be a more sophisticated level of autonomy, and this is going to be enabled only in certain areas where sufficient infrastructure will be available in order to guarantee integrity. We also expect that autonomous vehicles will be able to interact with non-autonomous vehicles, provided that the non-autonomous vehicles will have the basic functionality in order to be able to interact with them. At the minimum level of these capabilities, will have to include vehicle-to-vehicle communication and positioning with the required accuracy in order to perform this particular task. It will be expected that vehicles not retrofitted with these capabilities are not going to be allowed in order to operate in a particular areas of autonomy. We also expect that the other vulnerable users, such as pedestrian, motorbike, and bicycles, will also require technology in order to be able to interact with autonomous vehicles in this area. Otherwise, that areas with a special infrastructure will have to be designed or implemented in order to implement the interaction in those areas safely. For example, that crossing areas, and we have many examples that we had to implement today in the autonomous application that we've done in field robotics. Overall, we can say that this disruptive technology will transform the way that we move by making this more efficient and potentially achieving zero fatalities.
That's challenging and controversial as well. I think to get to a future scenario where all vehicles share some kind of information like status and intentions, there must be a standardization process across all the systems needed, right? Are you aware of any initiative in that sense? Do you think car makers will accept such standards, or will they have to be imposed to be mandatory by traffic administrations everywhere?
Okay, Javier, this is a very interesting question, and probably should start describing our experience with safety in the mining environment. As I mentioned before, that we started working in this area more than 10 years ago, and we introduced the concept of vehicle-to-vehicle communication and situation awareness. We also created flexible software protocols to be able to transmit a variety of information in order to achieve complete situation awareness. This approach, that was followed by others, users and their own software protocol. The fundamental problem was that all the approaches were not compatible with each other at the hardware level and at the software level. And there was no interest from the different providers of technology to make them compatible. Okay, this was possible since one operation or one industrial operation could afford committing to one particular type of technology, and then they were retrofitting all these vehicles with this technology. Obviously, this is not going to be possible in the automotive area. Fortunately, that there have been significant work with the standard during the last few years, and all the car manufacturers are actually agreeing on the standards. On the hardware side, there has been significant problem to set up the standard for communication, vehicle-to-vehicle and vehicle-to-infrastructure. This is usually refers at DSRC, dedicated short-range communication. There are also standards such as 802.11p, and they are already followed by a manufacturer of the technology. Today, we have just a large number of providers of the technology that have proven compatibility in many different long-term trials. So we are safe in terms of the hardware. There are also significant effort to standardize the software with the standard message described in a standard like SAE J2735. This now describes a list of messages, data frame, etc., in order to be interchanged between vehicles. There are also similar work done in Europe. The significant contribution in this area is that today, in anywhere in the world, we can design an application with one of these radios that generate a particular type of message, and we know that anyone else that supports this message will allow us to include us in their system. And this is basically a significant achievement compared to what happened in the past in mining application.
How about you, James? What do you think?
Yeah, I certainly agree with Eduardo, and he's given you a very good overview of the way things are starting to develop in this industry. Certainly the work that our group is undertaking at the moment has a focus on ensuring compatibility with these emerging standards. They are, of course, still emerging, so there's scope for the work that groups like ours are doing to influence how these communication standards and messages evolve. For example, we are working on inferring driver intent, but there's no easy way to transmit this information to other vehicles using the J2735 message set that Eduardo mentioned. Perhaps in the future, these standard message types might allow for this information to be exchanged if it's deemed useful enough. Conversely, we're also looking at how you can exploit the information transmitted using the J2735 messages. If we assume that cars in the future will be transmitting this own information, but nothing more, then what can we do with that slightly more limited set of information about other vehicles?
That's great, but how about safety? Do you see data privacy and security as a limiting factor for this? I mean, I guess anybody can imagine that hacking vehicles may become a very serious security threat if, for example, communications are not ciphered or there is not a reliable, constant access to some kind of, external certification authority. What do you think, Eduardo?
Okay, well, this is a very important topic, Javier. And there are a number of challenges that will need to be addressed in order to guarantee the acceptance and widespread of this technology. For example, that you mentioned one, that at one level we have privacy. That the moment that we have vehicles with an identity, with an IP, broadcasting information, we need to be able to guarantee that this information is only going to be used for certain purposes. This will require appropriate regulation to be passed by each state and federal government. At the technical level, there are a significant number of challenges too, probably many more than the one that we can address in this interview. For example, there are fundamental problems such as jamming, interference, spoofing, hacking. We already have some experience in those topics from military development, and in part in some civilian application. Nevertheless, the challenge in ITS will be significantly greater since the areas of operation will in general be public and accessible by a significant larger number of people.
Yeah, thanks, Javier. Look, I think Eduardo is correct about this. I think there will clearly be some big challenges to widespread adoption. Many of them are going to be technical, and many of them will be in areas such as politics and the law. I find discussions about how such systems could be deliberately interfered with, I find them very interesting. People talk of GPS spoofing or just sending out messages pretending to be a vehicle that isn't actually there. I don't have the full answers to these sorts of questions, but I think they might be overblown in some ways. Firstly, I think that solving some of these problems, or at least going part way to solving them, will be necessary to build a robust and reliable system, even when deliberate interference is ignored. For example, a vehicle with a failure of its positioning system will behave in much the same way as a deliberately spoofed vehicle. It will be transmitting state information that does not actually reflect reality. Anything that receives and uses this information will need to make some sort of assessment of the reliability of the information. And in fact, this is one of the things that our group is working on. How do you measure reliability of incoming information and account for it in your calculations? The second reason that I suspect deliberate malicious acts will be less widespread is that it's already possible to interfere with human-driven vehicles. You can go and throw oil on a road, and that'll do an excellent job of interfering with the traffic. Yet we don't see many instances of that sort of thing happening. Now, maybe I'm too much of an optimist about human nature, but I suspect that interference with autonomous and semi-autonomous vehicles, if it occurs, it will be quite isolated, and on the whole, societal pressures will actually tend to take care of a lot of these types of things because it will be seen as a profoundly antisocial thing to do.
Let's hope that.
I hope so too.
Okay, we are approaching to the end of this marvelous interview. Reading the potential applications of that database, you say that it can be useful to develop techniques to understand and predict driver behavior, what is necessary for autonomous vehicles to be successful. I think you mean to understand the behavior of drivers within not so verbose vehicles, and of course, manned, right? Can it be possible? Do you think driver behavior can be modeled in an accurate way that permits to focus his future maneuvers? And couldn't it be easier just to get rid of the human behavior variable, just letting all the cars to be automated?
Okay, well, probably this is the most comprehensive question, that in the interview. And perhaps we can start with a statement that there is no doubt that the future will see only autonomous vehicles working in the environment. The question is how to get there, and in fact, how we can facilitate the transition to this point. We have similar issues when we started working in automation in field robotics, and perhaps I can introduce a couple of concepts. One is a concept that we came up many years ago when we were working in automation that is called the island of automation. So we define this as an area where we only have autonomous vehicles. And this is the simpler solution. And we have a lot of experience in this area since we have many successful applications of this concept in field robotics. This is generally recognized as the preferred approach for the introduction of full autonomy in automotive application too. Furthermore, that there are, when you talk to many vehicle manufacturers, that they are implying or they are saying that full autonomy will only be enabled in particular areas. We could expect that we are going to have areas with all the infrastructure required in order to afford autonomous vehicles. In these areas, we are going to be able to guarantee all the things that we need in order to achieve a high integrity autonomy. For example, position accuracy, perception, and everything else. The next level of complexity is significantly larger. It's the one of mixing full autonomous system with non-autonomous vehicles. And in the past, in previous question, I was addressing this topic, assuming that we have cooperation, that we have vehicle-to-vehicle communication. And you would expect that the first introduction of autonomous vehicles or the mixing of autonomous with non-autonomous will require the non-autonomous vehicle to have these capabilities. Okay. In this case, let's assume that we gather enough experience in order to mix autonomous and non-autonomous capabilities with cooperation, and we want to go one step further and allow vehicles that are not retrofitted with this technology. This is becoming a much more difficult task because in this case the cooperation may not be able to achieve in a smooth and predictable manner. So in this case, the prediction of intention become essential, as well as other information in order to interact safe. For example, and this is an example that I usually making presentation is that we already have implementation of very sophisticated technology like adaptive cruise control, that this device have a sensor that monitor the truck in front, and basically they actually tracking the behavior of the truck in front in order to maintain a constant distance to this truck or vehicle. You also have devices, that monitor the position in the line and can actually tell you when you are close to the line, or even correct the position of the vehicle in order to maintain your vehicle in the center of the line. So with these two technologies, you may believe that you are ready in order to implement autonomy. But autonomy is much more difficult like that, because the person that is driving a car is actually monitoring the environment all around the vehicle. For example, if I see a car coming through the ramp, just by having a glance of this vehicle, the operator can infer some information about the intent of this driver. He's coming too quick crossing the lines, he can infer that this driver is going to be in his line in a few seconds. Okay, so basically, we need to be able to introduce the perception in the vehicles, and not only the perception, but we need to include, we need to develop the algorithms that we can infer in turn from this perception. We believe that we will have enough information in order to be able to predict driver intention with the level of uncertainty required in order to implement safe interaction. There will also be a scheme in place that in case the prediction of intention fail, the car will have some other behavior like braking, collision avoidance maneuvers in order to attain this exemption. Overall, we are absolutely certain that driver will be much safer when all these systems are in place.
That's great. How about you, James? Do you share Eduardo's view on it? For example, regarding a fully automated future for all vehicles? I bet some of our listeners wouldn't agree on that, but you mentioned you are an optimistic, right?
Absolutely. And I think a future where all vehicles are able to drive themselves is certainly an optimistic one. I personally look forward to it. I think Eduardo's right. I think it is inevitable because it will just have such a profound effect on the way society works. We will become so much more efficient and we'll become so much more safer. And that's one of the things I think is going to make this inevitable. And as Eduardo said, we have a lot of experience in this particular area in terms of introduction of autonomous systems. And I think the way that Eduardo has outlined it is pretty comprehensive, and I would agree that that's the way things will be going in the future.
Okay. Well, this is it. Thank you both very much for your participation. It's been a very, very interesting and enjoyable interview. Thank you.
Thank you very much, Javier. It's been a pleasure talking to you.
Okay, thank you very much, Javier, and it has been a real pleasure talking to you.
Goodbye.
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 Bad news. We're closing this episode. It's time to end it. Please feedback us with your comments and improvement ideas. We love when we notice you are actually there. And stay tuned because we are already working on a new episode for our special audience. This podcast is sponsored by the IEEE Intelligent Transportation Systems Society, website designed and managed by the Innovation Center for the Information Society at the University of Las Palmas de Gran Canaria in Spain, soundtrack developed by Rubicon, language advisory by Manuel Arbelo, and Professor Sean Williams from Clemson University, South Carolina. We'll be back soon bringing you again the cutting edge of science at the Intelligent Transportation Systems Podcast. Thanks for listening and drive safe.